Have you ever really truly stopped to think about what happens when you hit send on an email? I mean, it's pretty wild. A piece of your digital self just vanishes. And then in the blink of an eye, it reappears on a screen halfway across the planet. Today, we're going to pull back that curtain. We're going to follow a single, lonely data packet on its incredible journey across the invisible highways of the internet. It really all comes down to this one question, doesn't it? It feels like it should be impossible. A message finding one specific person among billions of devices. And it does it in less time than it takes to snap your fingers. Well, I'm here to tell you it's not magic. It's actually a system of incredibly brilliant, surprisingly simple rules. And by the time we're done here, you're going to understand exactly how it all works. All right, so what's our game plan for cracking this code? First, we're going to talk about the internet's postal service. You know how every device gets a unique address? Then, we'll see how your own computer takes its very first step online. After that, we'll dive right into the router's dilemma, which is really the heart of the decision-making process. Then, we'll figure out how these routers build their maps of the digital world. And finally, we'll put all that knowledge to the test. Let's do it. Okay, first things first. To send anything, anywhere, you need an address. Simple, right? Well, the internet, at its very core, runs on that exact same principle. So let's start there, with an analogy that's going to make this whole thing click. Just imagine a global post office. Every single thing connected to the internet, your phone, your smart TV, the server hosting Netflix, it all has a unique address. We call it an Internet Protocol address, or IP address for short. Without it, your device is basically off the grid. The internet simply wouldn't know where to deliver your data, just like the post office can't deliver a letter with no address on it. It is the fundamental ticket to the game.
Now, here is where the absolute genius of the system starts to shine through. An IP address isn't just a random string of numbers. It has a structure, a hierarchy built right into it. The first part is the network address. You should think of this like a zip code or a city. It gets your data packet into the right general neighborhood. The second part, the host address, is way more specific. That's like the street and house number that pinpoints the exact device in that neighborhood. This simple split is what makes the entire global internet possible.
So you might be asking, why bother with the split? Why not just give every single device its own totally unique number and call it a day? Well, let's go back to our postal worker. Imagine you're a mail carrier in New York City, and to do your job, you have to memorize the exact street address of every single house in the entire world. It would be completely impossible, right? And that's the whole reason. It's all about efficiency and what we call scalability. By splitting the address, the routers, who are the internet's mail carriers, don't have to carry that impossible burden. They don't need to know where your specific laptop is. They just need to know how to get to the zip code, the network that your laptop is on. Once the data packet gets to the right neighborhood, a local router can handle the final delivery. It's this design that lets the internet add millions of new devices without grinding to a halt. Okay, so our data packet knows where it's going. It has a destination address. But what about us? Before our computer can send anything, it needs its own address. And it needs to know where the local post office is. So how does it get all that info and take that first step out the front door and onto the web?
Just think about it for a second. You walk into a coffee shop, you tap on the Wi-Fi network, you type in the password, and bam, it just works. You're not sitting there manually configuring network settings. Something happens automatically, behind the scenes, that gets you all set up. So what is that something?
That magical something has a name, DHCP, or the Dynamic Host Configuration Protocol. The best way to think of DHCP is as the network's super-friendly concierge. When your laptop connects, it basically yells out into the network, "Hey, I'm new here. Can somebody get me set up?" A DHCP server, which is usually just a piece of software running on the Wi-Fi router, hears this call. It then comes back with a welcome package of information. It says, "Welcome to the network. For your stay here, this is your temporary IP address. And by the way, if you need to send a message to anyone outside of this local network, give it to me. I'm your default gateway." That default gateway is absolutely critical. It's the one and only door out of your local coffee shop network and onto the giant, sprawling internet.
So our packet has been created, addressed, and handed off to the default gateway, that local router. And right here, this is where the real intelligence of the internet finally kicks in. This router and every single router that our packet will meet on its journey has to make a critical decision. See, at the heart of every router is basically a map, but we call it a forwarding table. Now, remember, this map doesn't list every single house in the world. That's not scalable. Instead, it contains a list of network prefixes, those zip codes, and for each one, it knows the very next router to send the packet to. So when our packet arrives, the router looks at its destination address, quickly checks its map, and in a fraction of a second, makes a decision and forwards it along.
And this is a fantastic question because it happens constantly. A big network can be divided up into lots of smaller subnetworks, so it's totally possible for a destination address to match a very general route for the big network and a much more specific route for one of the smaller ones. So what does the router do? Does it get confused? Does it just pick one at random?
Nope, there's a rule. In fact, you could call it the single most important rule in all of internet routing, the longest prefix match. The logic is so simple and so elegant. The router looks at all the routes that the destination could possibly fit into, and it always chooses the most specific one. And in networking, most specific means the one with the longest network prefix. It makes perfect sense, right? If you're sending a letter, a full street address is always better and more specific than just the city name. The internet works the same way.
This table right here shows the rule in action perfectly. Let's say our packet is trying to get to the IP address 192.168.1.140. The router checks its table and finds two entries that match. The first one, 192.168.1.0/24, is a pretty big network. That /24 means it has room for about 254 devices. Our destination definitely fits in there. But then it sees the second route, 192.168.1.128/28. That /28 represents a much smaller, more specific network with room for only 14 devices. Our destination also fits perfectly in this little group. So which one does it choose? Well, 28 is a longer number than 24, so the longest prefix match will kick in. The router sends the packet down the more specific /28 path. It's just more precise.
Now, you might be thinking, hold on, the main routers on the internet have tables with like a million routes. Doesn't it take forever to search through all of them? And you'd be right if it was just a simple list. But they use incredibly clever computer science, specifically a data structure called a Patricia tree. You don't need to know the details, but what it does is amazing. It allows the router to find the best path, not by checking every route, but by looking at the destination address one bit at a time. For a standard 32-bit IP address, this means it can find the longest prefix match in a maximum of 32 steps. It doesn't matter if the table has 10 routes or a million, it's always just 32 steps. That incredible efficiency is what allows the internet's core to operate at mind-boggling speeds. So these routers have these super fast, super efficient forwarding tables. But where in the world does that information come from? An engineer isn't sitting there typing in a million routes by hand. The internet changes every single second. That would be impossible. Well, the answer is the routers build the maps themselves. They're constantly chattering with their neighbors using special languages that we call routing protocols. They're basically gossiping. One router might say, hey, just so you know, I can reach these 10,000 networks. Its neighbor hears that, adds it to its own map, and then passes that information along. It's this massive, decentralized, collaborative effort that maps the entire internet, and it does it in real time. Now, these routing languages or protocols basically come in two flavors. When routers are all inside the same network, like all the routers on a university campus, they use an intra-domain protocol, like OSPF. Here, the goal is really simple. Find the absolute fastest, most efficient path to get from point A to point B inside our own network. But when you need to connect that university to the rest of the global internet, you need a different kind of protocol. That's where inter-domain routing comes in, and the big one here is BGP. And with BGP, the goal isn't just about speed anymore. It's about business. It's about policy. Who do we connect with? How much does it cost? BGP is how big networks like Comcast and Google negotiate how traffic flows between them.
All right, that was a whirlwind tour. We've seen how our packet gets an address, how it finds the front door, and how every router on its journey makes the smartest choice possible. Now let's put it all together and see if we can apply what we've learned to a few quick questions.
Let's break these down one by one and really connect the dots. First question, why split IP addresses? The key concept here is scalability. Remember our postal worker? They can't memorize every address in the world. By splitting the IP address into a network part and a host part, routers only need to know how to get to the right network or zip code. So the answer is clearly C, to avoid storing every host IP in routers. It's the only way the system can grow. Second, how do PCs get IPs automatically? This is all about network configuration. When you connect to that coffee shop Wi-Fi, you're not doing anything manually. That's because DHCP, our network concierge, is doing all the work for you. It hands you your IP address and tells you where the default gateway is. Third, what's the protocol for routing within a domain? This is testing if we know the difference between our two types of routing. When all the routers belong to the same team, like inside a company, their goal is just speed. And the protocol they use for those local maps is COSPF. BGP is what they use to talk to other companies. And finally, our last question, how do you decide if multiple routes match? This gets to the heart of forwarding logic. This is the router's dilemma. When faced with two or more possible paths, it needs a tiebreaker. And that golden rule is B, the longest prefix match. The router will always, without fail, choose the most specific route possible.
And just like that, what seemed like pure magic is really just a beautiful, logical step-by-step process. It starts with an address, it finds a gateway, and then it's guided on a journey by thousands of routers all making split-second decisions based on that one simple rule: always take the most specific path. So the next time you hit send, take a moment, picture that incredible invisible journey, and maybe give a little nod to the elegant system that makes our connected world possible.